Good morning and good afternoon, everybody. Welcome to today's webinar. Thank you all for joining us. My name is Axel Stürmer. I'm the marketing manager in the German office of Thorlabs, and I will be the moderator today. Today's webinar is the second in a series of 4 webinars covering light characterization tools and methods. Manfred Gonnert, team leader of the Light Detection and Analysis R&D group at Thorlabs Germany, will talk about the basics of photodiode. He will also review different types and materials of photodiodes and how to operate them. After graduating as an electronics engineer from the University of Applied Sciences in Munich, Manfred joined Thorlabs in 1991 as a production engineer. Later, his role evolved to include the exploration of power and energy meters, as well as other sensor products. In 2018, he became head of the Thorlabs Light Detection and Analysis team. Manfred will be presenting for approximately 45 minutes with a subsequent Q&A session. You can ask questions anytime by clicking on the Q&A tool at the top right corner of the window. We will collect your questions and discuss them after Manfred's presentation. I hope you will enjoy the webinar, and I am happy to let Manfred take it away.
Axel, thanks for your introduction. I also welcome you all, and then let's go through the agenda. Just a second. As Axel mentioned, we will review how a photodiode works and how it can be connected to an electrical circuit. We will continue with the detector integration and then in an experimental setup and show what limitations are to consider. Then we'll describe the functionality of avalanche diodes, single photon counters, and balance detectors, highlight their advantages, and show examples where they can be used. To start with, we should answer a few questions that help guiding to the selection of the most suitable detector. First limitation in the wide field of detector choices can be made if you start from your laser wavelength. This enables the suitable detector material to be found quickly. As a next, whether the optical signal is modulated and how fast leads us to the required detector bandwidth. The detector active area should match with the spot size of your laser beam, and an estimate of laser power helps you to select the detector sensitivity and whether it needs an attenuation or an amplification. As last point, the application setup determines the available space for the detector element and the proper mounting to your optical table. Before we see the detector in its application, let's take a brief look at how a pin photodiode works. That is the commonly used kind of diode in most detectors. The principle behind every semiconductor photodiode is to turn the photon to an electrical energy. Photodiodes usually are built as p-n junction. That means you have a p-dotted region and an n-dotted region with an intrinsic weak dotted region intermediate layer, the so-called depletion zone. When now photons hit this layer, electrons and holes are excited and directed to the corresponding zones. This leads to a flow of electrical current. Photons with a too short wavelength get absorbed in the upper layer or protection glass of the diodes, so no current flow will happen. And longer wavelengths get transmitted also without electron generation. A performance key indicator of photodiodes is the quantum efficiency. This describes the ratio between activated electrons by incident photons. For an ideal photodiode, the internal quantum efficiency is close to 100%. The responsivity of a photodiode corresponds to the external quantum efficiency at which all photons that reach the diode surface are used for the calculation, including those that don't reach the charge carrier zone because of reflection or absorption. The responsivity is defined by the current flow per incident power. The final formula shows the conversion from the quantum efficiency to the responsivity. So now coming back to our first question about the operating wavelengths. For all applications with visible or near-infrared lasers, a silicon photodiode will be the best choice. These are cost-effective, even with large active areas, and can be used from the UV up to 1064 nanometer laser wavelengths. For telecom, wavelengths range in 1310-1550 nanometers. Germanium or indium gallium arsenide diodes can be used. The indium gallium arsenide diodes are also available with an extended version up to 2.5 micrometers. Other materials are silicon carbide and gallium phosphide for the UV, and indium arsenide antimonide or mercury cadmium telluride for the infrared up to more than 10 micrometers. We learned in the previous slide that photodiode material can be transmissive for long wavelengths. This allows stacking photodiode chips to broaden the wavelength range. In this example, a silicon photodiode chip is built on top of an indium gallium arsenide photodiode chip to cover the full wavelength range from 300 nanometers up to 1700 nanometers. When it comes to the question of sensitivity, especially on the low end, the noise level defines the minimum measurable power. There are several sources that are contributing to the photodetector noise. This can be Schottky noise from the dark current, the thermal noise from the shunt resistance, and in addition, the amplifier noise. This is a voltage and current noise in the following amplifier. The noise equivalent power, or NEP value, is used to combine these noise sources to a measured variable. The NEP defines the incident optical power required to obtain a signal-to-noise ratio of 1. To have comparable numbers, the NEP value can be a value for the detector element as well as in combination with an amplifier. It is measured in watts per square root hertz. Another parameter is the detectivity, mainly used for the detector element itself. This is the reciprocal value of the NEP. Very often one can find the specific detectivity in detectors data sheets abbreviated as D star. This is a NEP related to the detector area, and this value allows the noise comparison between detectors with different sizes. The NEP on one hand can be reduced by a longer integration, or on the other hand, it will get larger the faster the signal to measure is. To give an example, when detecting a signal in a 1 megahertz bandwidth with a NEP of 1 picowatt per square root hertz, the optical power required for a signal-to-noise ratio is 1 picowatt times square root 1 million, means 1 picowatt times 1000, and this gives a minimum measurable power of 1 nanowatt. Usually the NEP is considered constant up to the cutoff frequency. However, the Thorleb spectrum analyzer measurements with full bandwidth show slightly rising NAP values up to the bandwidth limit in the datasheets. In our detector datasheets, we are specifying this higher value at the 3 dB limit as the NAP value. There are more insights to photodiodes and NAP. These can be found on the Thorleb's website. There are tutorials, app notes, white papers to this topic. Now, to understand the limitations in speed or sensitivity, we need to have a look how a photodiode behaves from an electrician's technician's point of view. Starting point is the current source that enables the flow of electrons caused by the incident photons. Going further, there is a junction capacitance parallel to the current source, and this is associated with the PN junction. It strongly influences the photodiode's frequency response. Increasing the active area, the larger the junction capacitance, the lower the photodiode. As next, there is a parallel resistor that is called shunt resistance. This resistance is infinite for an ideal photodiode, but it depends on the material in the real life. It may range from ohms to mega ohms. The lower this shunt resistance is, the higher the noise and dark current of the photodiode. As a last element, there is a series resistance that arises from the contacts and the wire bonds of the photodiode and is used to mainly determine the linearity of the photodiode under zero bias condition. If there aren't excessively long connection cables, it can usually be ignored. Now that we know the basics about the photodiode itself, we want to use it in an electrical circuit to measure the magnitude of the photocurrent. There are two ways to operate a photodiode. The photovoltaic mode means a forward operation against the load resistance in the nonlinear range of the photodiode. To give an example, like the operation of a solar cell. In our case here, where linearity is desirable or even more mandatory, the better expression is zero biased mode. In that mode, in combination with a low load resistance, like given by the here shown transimpedance amplifier, a linear operation with very low noise and very low dark current is possible over several decades of photocurrent. The limit here is some 0.5 milliamps up to 8 milliamps of photocurrent, strongly depending on the photodiode. This mode is usually taken for power measurements. On the right side, the photoconductive or reverse biased mode increases the depletion zone and therefore the quantum efficiency. In addition, the junction capacitance gets smaller and therefore higher bandwidths are achievable. The photodiode can so be operated in a linear way up to higher photocurrents. To get a voltage signal from a photodiode, a simple method is just connecting a load resistance. The output voltage can be easily calculated by the photocurrent flowing through the resistor. However, the value of the resistance must be chosen carefully. If it is too low, the frequency response is better, but the signal is very weak. If it is too high, the input resistance of the measurement device will load additionally this resistance, and the noise will increase and the bandwidths get lower. For best matching, the load resistance should be 50 ohms. when the signal strength allows a measurement. To overcome this issue, it is better to use a transimpedance amplifier that converts current to a voltage. Transimpedance amplifiers have a virtual ground on the signal input, so the diode is short circuit. The current through the feedback resistor is equal to the photocurrent, so the output voltage can be calculated by the photocurrent times the feedback resistor value. Both schematics work in reverse biased and zero biased mode. Additionally, an AC coupling can be achieved by connecting a capacitor in line with the photodiode. This blocks out the DC current generated by the continuous wave power level, so that just the modulated signal gets amplified. When selecting an operational amplifier, the gain bandwidth product is an important parameter that can be found in the op-amp datasheet. The gain bandwidth product with the unit hertz is a constant that defines the maximum achievable bandwidth at gain 1. When looking on the specifications of one of the Thorlabs PDA amplified photodiodes, you can see that the higher the gain, the lower the bandwidth, and therefore the slower the response. The gain of the detector is dependent on the feedback resistor of the transimpedance amplifier. CD is the sum of the junction capacitance and the feedback capacitance. So as an example, a gain of 10 means a 10 times lower bandwidth. Bandwidth and photodiode rise time are connected by a simple equation that allows a convenient way to estimate rise time when the bandwidth is known. To remember, the bandwidth limit is reached when the output voltage drops to 70% or minus 3 dB. The rise time of a detector is the measured pulse response between 10 and 90% of the signal. Photodiodes are usually pretty robust when following some precautions during assembly and operation. During assembly, treat them as an electrostatic device, keep soldering times short, avoid mechanical stress on the leads, and protect the active area while mounting or soldering. Once the diode or detector package is in place, take care to not exceed the following two limits. The first one is obvious. Exceeding the damage threshold will irreversibly damage the photodiode. The datasheet will not always state the damage threshold, but a photodiode can typically last some 100 to 1000 milliwatts per square centimeter. Please be aware that the damage threshold is an irradiance limit. This can be reached even with assumed small power levels when focusing a beam. The 1 watt per centimeter square are, for example, exceeded with a 10 milliwatt signal at 1 millimeter beam diameter. In opposite what we saw here, the diode can even die without visible traces. The saturation power limit is important to stay in the linear range and therefore getting predictable measurement results. The linear range is dependent from the photodiode itself, the load resistance, the bias voltage, and the beam size. Typical values are here single-digit milliwatt values. To practice a short demonstration how to calculate the saturation limit from the datasheet, assuming our operating wavelength is 532 nanometers. First, we have to solve the equation to the saturation power. As next, we need to take the responsivity value for 532 nanometers from the responsivity graph, the 0.27 amps per watt. Assuming a 50 ohm termination, the gain is given to 5000 volts per amp. Put that to the gain, and the maximum output power is 5 volts. We have it here, 0 to 5 volt for 50 ohm. As a result, we are getting a saturation limit of 3.7 milliwatts. To finally answer the question about system integration, a quick foray through the portfolio. It starts with bare photodiodes that are best to integrate in tiniest spaces. Skill in soldering, assembly, and electronics circuitry is required. Next level are the mounted photodiodes with their SMA or BNC connectors for convenient connection. The aperture threading fits to all Optomax setups. Both bare and mounted photodiodes can be connected to one of the M series transimpedance amplifiers. There are various models with different gain levels, bandwidths, or optional bias available. They feature a BNC in and output and a 5-volt, single 5-volt supply. When high bandwidth is required, the DET or DMX series with built-in bias voltage are a good choice. The series that has free space and fiber-coupled models is intended to work with external 50 ohm load resistance. The extensive amplified detector series covers the UV to mid-IR wavelength range. High fixed or switchable gain or high bandwidth versions are available here. In all shown models on this side, the photodiode chip is exposed. For detecting higher power levels, an external attenuation must be attached to protecting the diode and avoiding saturation. So, neutral density filters are the most economic way to attenuate a beam. The attenuation either happens inside the filter material or on a deposited reflection layer. These filters work well up to low digit, single-digit watt range. Integrating spheres homogeneously distribute the incoming light over their surface. A small portion of this light can be picked up on the exit port of the sphere. The material can handle up to tens of watts. Beam splitters are available with different splitting ratios and coatings, even for short pulsed beams. A further very effective way to largely attenuate a high power laser beam is the prism attenuator. Its design with wedged glasses works like two stacked beam splitters while keeping the beam polarization state. To sum up the pin diode related section, we cover the detector material that is responsible for the spectral operating range, the detector size that should be large enough to collect the complete beam, but small enough to reduce noise and increase the speed, the amplifier gain with the trade-off between gain and bandwidth, the need of bias to trade between linearity and speed or lowest noise. As last, the integration requirements of the detectors in the optical setup. A large field of application is already covered, but what can I do when I need both low noise and high speed, or high sensitivity and high speed, or all three of them? This question leads us to the advanced applications with avalanche photodiodes or balanced photodetectors. Starting with a special type of photodiode, the avalanche photodiode. Like every photodiode, photon energy will be transferred into an electrical energy. When we look to the schematic diagram, we can find a new layer, the p-dotted avalanche region. This, when a negative bias voltage is applied to the diode, increases the electrical field in this region. When now a photon enters the depletion zone, each electron excites multiple other electrons by the avalanche effect. Thus, the responsivity can be 5 to 100 times higher compared to a pin photodiode. The multiplying factor M increases with the level of the bias voltage. Zero bias means M equals to 1. Downstream transimpedance amplifiers gain multiplies with the M factor. Various applications require different specifications. Therefore, Thorlabs provides APDs from highest gain and lower bandwidth up to lower gain and highest bandwidth. These APDs provide several useful features like temperature compensation, variable gain options, and possible fiber coupling via our common aperture threading. Finally, a look to a couple of applications. So APDs can be used in the process control for laser machining applications like welding, drilling, cutting, or the additive manufacturing. The reflected beam gets measured often in different wavelength ranges to monitor the quality of the processing. The setup shows a machining laser, a scanner, a dichroic mirror, and a monitoring APD. Starting our application, the first run shows a perfect signal, which was triggered by the flame that was created. Now let's defocus the workpiece and release the next pulse. We can see that the laser doesn't have the energy to shape the material and the reflected signal is absent. So the process failed. This one-dimensional method is mostly sufficient and much cheaper than two-dimensional or three-dimensional methods with cameras or OCT. Sometimes the methods get combined for this process monitoring. Further, the amount of data exchange and processing is minimized with just having one signal. APD detectors can be used in many applications where high speed and high gain is necessary. To name some examples, fluorescent imaging, DNA sequencing, flow cytometry, and general sorting and recycling. You always measure some reflected light or some light going through a sample. So another special kind of avalanche photodetectors can be used for single photon counting. To explain the working principle, we are looking to the diode current voltage curve that is separated in three areas: the breakdown area, the reverse operation area, and the forward operation area. For pin photodiodes, the forward operation would correspond to the photovoltaic mode and the reverse biased operation to the photoconductive operation. Now let's come to the step A and the speciality of single photon APDs, that they can be operated beyond the breakdown voltage, also called overvoltage. This mode is called Geiger mode. Here the diode remains in a metastable state until, and this leads us directly to step B, a photon arrives and frees charge carriers that trigger an avalanche of electrons. Once the current pulse has been detected by the following electronics, we come to step C, where a quenching circuit lowers the bias voltage below the breakdown voltage. During this quenching time, which is known as dead time or recovery time of the diodes, the APD is insensitive to any other incoming photons. After the process of the dead time is over, the APD is loaded again and ready for the next photon. To name some key specifications of single photon counters, the photodiode efficiency is the most prominent. It compares to the responsivity of a photodiode and describes the ratio of detected photons to all incident photons. The maximum reachable photodiode efficiency depends on the level of overvoltage. The higher this voltage, the higher the PDE. However, this goes hand in hand with an increase in the dark count rate. This rate results from counting results without incident light caused by spontaneous emission while the diode is biased. A typical magnitude is in the range of some tens per second up to thousands per second. To lower the dark count rate, single photon APDs are actively cooled by usually dual stage tech elements. The recovery speed or dead time is the time to re-trigger the system. That means until the electrical field has rebuilt. At that time, no photons can be detected. The dead time is in the single nanosecond to hundredths nanosecond range. As a last topic, to get a feeling for photon quantities in radiometric units, the conversion will be explained. The number of photons observed per unit time is the photon flux or count rate. To get an equivalent in optical power, the photon flux needs to be multiplied with the energy of one photon. And the energy of one photon is the Planck constant multiplied with the speed of light and divided by the wavelength. Example for light with 660 nanometers, a dark count level of 100 per second corresponds to 0.03 femtowatts. A rate close to the saturation limit of 10 millions per second corresponds to 3 picowatts. The next slide gives an overview to the Thorlabs single photon counting devices. The first unit, the SPCM series, has its highest detectivity in the 500 nanometer range and comprises a complete counting unit and a convenient PC operation via USB. The soon available SPDMA has a sufficient PDE over broad wavelength range, especially in the near IR. The user can optimize between low dark current and high PDE, low dark current, the lower curve, and high PDE, the upper curve. It additionally features a large active area of 500 microns, a small footprint without the necessity of fan cooling, and simple fiber access. Here an example that shows single photon counting in a contemporary application, the quantum cryptography. Regular encryption is breakable, but not the quantum cryptography. The example demonstrates the simplest case of quantum cryptography, the quantum key distribution. It uses the Heisenberg uncertainty principle to prevent eavesdroppers from cracking the code. The setup consists at the transmitter side of a single photon source and a polarization rotor for 4 states. On the receiver side is a polarization rotor for 2 states, a polarizing beam splitter, and 2 single photon detectors. Alice at the source side sends bits which get encrypted by the polarization state. Both 0 and 1 have 2 polarization states, either vertical and right linear for 1, or horizontal or left linear for 0. The receiver Bob set the basis for either rectilinear, horizontal vertical, or diagonal left right linear, and receives bits that can be correct or not. After that, tells Bob Alice his space, his choices for each bit. Alice tells Bob the matching bits to keep. And with that, a secure key gets generated by sifting the bits that were detected correctly. To dive deeper into the quantum cryptography, I can recommend to scroll back in the recorded webinars to March 11. There is one that covers quantum cryptography, educational kit, and all the technical details behind. Other applications for single photon counters are quantum physics experiments and optics experiments, time of flight measurement, and also fluorescence lifetime measurements. In the last step, we want to get to know the advantages of balance detection. Balance detectors are capable to detecting small differences in optical power between 2 signals by suppressing the common input fluctuations. The key elements are 2 very well-matched photodiodes due to their capacitance and responsivity. The animation shows a signal from one light source that enters the application, where it gets distributed into 2 paths. In the simplest way, a portion of the original signal goes to one input, the other portion with any kind of altering like modulation, delay, or attenuation goes to the other input. With balance detection, the photocurrents of the 2 diodes get now subtracted from one another and amplified with the following 2-stage amplifiers to the RF output. Since the noise on both inputs has the same magnitude and shape, it gets eliminated to a large extent, and only the signal gets amplified. The monitor outputs can be used to observe the signals of the individual inputs. And to specify the quality of suppression, there is a common mode rejection ratio. This describes the magnitude the balance detector is capable to suppress identical input signal on both input channels. The common mode rejection ratio is specified as a ratio in dB. Thorlabs offers balance detectors for a variety of applications. They can be divided in fiber-coupled devices with very flat frequency response up to 2 GHz bandwidth, free space versions with large active areas up to 5 mm silicon and up to 3 mm InGaAs photodiodes. They have common mode rejection values up to 40 dB by 1 MHz bandwidth. A model with 100 MHz bandwidth is coming very soon here. In addition to the convenient lab balance detectors, there are the compact PCB mountable and fiber coupled detectors up to 2.5 GHz bandwidth. Their low footprint makes them attractive for system integration. To name some applications suitable for balance detection, there is LiDAR that can be used for both distance and speed measurements. The demonstration setup shows a pulse modulated fiber light source, a collimator that functions both as transmitter and receiver, and some couplers and a circulator that distribute both the transmitted and received signals to the detector inputs. By measuring the amplified signal of the transmitter and receiver, speed and distance of an object can be measured simply by the delay between sent out pulse, for example, and received pulse. A real-life application for this is wind speed measurements. In that case, the objects that reflect the laser beam are aerosols in the clouds. Many other applications can be found in the interferometric detection. In interferometers used for optical coherence tomography, one can substantially improve the noise performance with balance detection. The balance detectors receive the light from the two outputs of the beam splitter, where the signal beam is superimposed with a reference beam. The difference of the photocurrents delivers the wanted interferometric signal while suppressing intensity noise of the light source. Such techniques also are used for optical heterodyne detection in various other applications. Balance detectors can also be used in optical time domain reflectivity to measure the back reflection in fibers, or for terahertz detection, where the terahertz radiation gets converted to light with electro-optical crystals, linear polarized and split by a Wollaston prism to the detector inputs. Finally, I want to give you an overview to the various photodetector series on the Thorlabs website. It starts with separated photodiodes and amplifiers that can be used in a variety of applications. One example is attaching the photodiode to an integrating sphere and have the amplifier connected via a BNC cable. The biased DET series has its strength with highly modulated signal up to the gigahertz bandwidth or even higher. And there is a large variety of amplified detector packages. Let's start with the PDA series for general purpose with fixed or variable gain. The PDF series with 1 teravolt per watt transimpedance gain for lowest power levels down in the picowatt range. This can be used, for example, in flame detection or film applications. Mostly too slow for film application because the bandwidth is very low, but for the flame detection. And the amplified Mercatel detector series for the mid-IR, for example, for mid-IR spectroscopy. The DXM and RXM series with fiber-coupled high-speed indium gallium arsenide detectors opens the field for telecom applications with gigabit transfer rates. As we have seen, the Avalanche series with high bandwidth and high gain for the process monitoring, for example, or other low light, high speed applications. Or the single photon counting series, for example, quantum photonics. And to finish, the detector series, a whole range of balance detectors for maximum noise suppression. So we got to the end, and I thank you for watching and listening. Just to point out the upcoming webinars in light characterization series that will start in September with beam characterization, and in November about polarization measurement. And now I hand over to Axel, and it's time to address a few questions if you have.
Thank you very much, Manfred, for this presentation. Just like you said, we now have time to answer some questions. A couple of questions have come in, and I'll just start off with two about the damage threshold of photodiodes that you covered in one of the earlier slides. So there's two questions. The first would be, do photodiodes get damaged if a laser pointer's beam is irradiated on it? I interpret this as a CW signal just being hit at a sensor active area.
With a standard laser pointer. I think you cannot damage it as long as it is a eye-safe laser pointer. The beam is too large and the energy density is much too low for damaging anything.
Okay, but if it comes to like focusing the laser pointer, you could potentially run into problems, right?
Yes, but it's not very likely.
Okay, thanks. Another question also concerning the damage threshold is, what is the relationship between the laser-induced damage threshold, LIDT, and the pulse width of a laser pulse? I think this refers to the fact that you have only mentioned a rough guideline for CW lasers being at around 100 milliwatts per square centimeter. Any guidance for pulsed signals there? Or?
Yeah, it's actually a very low level. I think we really specify some microjoules per square centimeter. Of course, the shorter the pulse and the higher the energy density, it can get to problems. It depends on the repetition rate, whether the photodiode is fast enough to follow the pulse or not. This is one of the crucial things for this pulsed damage threshold.
Okay, thank you. Another one would be, do you also offer, or do we also offer calibrated photodiodes, and are there any limitations to what we could calibrate or not?
Yeah, we usually have calibrated photodiodes. There are a couple models on the website. We can also calibrate some special photodiode packages like this mounted photodiodes. The only limitation is that the active area may not too small. So we calibrate spectrally with a monochromator. And here is the limit of the output beam size of this monochromator that is in the 1.5 millimeter range. So every photodiode larger or equal to 2 millimeter active area can be calibrated.
Okay. Another question that just came in is, I assume a rather general one, and one that could be answered like for an hour or so, but maybe just some brief thoughts on this. What is a good way of improving signal to dark current ratio?
Signal to dark current ratio. Yeah, we have to start with should this dark current, is this dark current a background light or is it really dark current? Starting with this one, okay, background light should be blocked as good as possible. When we have the real dark current, the zero biased mode reduces it very, very to the zero end. In biased mode, it can get problems, and there I would recommend a balance detection where you balance out this dark current noise.
Okay. One question going back to the calibration of photodiodes. Sabi is asking, how well does a calibrated photodiodes calibration hold up over time?
Normally, as long as any of the power meter sensors, so we recommend a recalibration, a yearly recalibration. Typically, it holds much longer. As long as the surface of the diode is kept clean and free of dust or other disturbing external attenuations.
Thank you. And maybe one last question for now. I know that there's that many of you have asked maybe more complex questions, and we got our internal tech expert already reviewing them, and they would probably just be too much for this scope. So feel assured that we will reply to all of these questions as long as you leave us any way of reaching out to you if you have not received a reply until now. And just so one last question for the general audience. For balanced photodetectors, should the two inputs have the same power?
Yes. As you have seen, the power difference gets the amplification. So if the two powers are far different, you will run into the saturation of the output.
Okay. Thanks a lot, Manfred, for answering all of these questions, and thanks to all of you who joined for asking these questions in the first place. It's good to have this interactivity through this webinar. If anything has been left unanswered, or if you have any questions later on, feel free to reach out to us at any time. You can contact your local tech support team. The respective email addresses and phone numbers can be found on our webpage under services, technical support. And if there's any questions concerning this specific webinar, they will be forwarded to us, to Manfred and me, and then we can discuss this in more detail.